Welcome viewers. In this video we will see the construction of three-phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, construction of three-phase induction motor. This induction motor consists of two main parts are available. The first one is the stationary part called a stator. Stator is a stationary part in which the three-phase winding is placed. Stator is a stationary part in that stator windings are available. The rotating part is called a rotor, which is connected to the mechanical load through the shaft. The load is connected through the rotor. This rotor also having the winding or copper bars. So mainly we have the two parts, stationary part stator and rotating part rotor. Now we will see the diagram. So this is the overview of the three-phase induction motor. So this is the outer part is the stator. This portion is nothing but a stator slot. The windings are placed in the places. These slots are provided for placing the winding, stator winding. So this inner part is the rotor, rotating part, through which the load is connected. This is the shaft. This rotor is placed in the shaft. So here also the slots available, the copper winding or copper bars are placed in the rotor. So the stationary part stator having the stator winding, the rotating part rotor that also having the copper winding or copper bar. This rotor is placed in the shaft. The load is connected to the load through the shaft. Now we will see the description. It has laminated construction made of stamping which is 0.4 to 0.5 millimeter thickness. It's a laminated. This iron core is highly laminated in order to avoid the eddy current loss. So it is not a single piece. The n number of thin sheets are combined together, laminated and combined together with a thickness of 0.4 to 0.5 millimeter thickness. The stamping have the slot on the inner periphery to place the stator winding. So this is nothing but this is the core, laminated core. The slots are available. In that slot only the stator winding is placed. The stamping is made up of silicon steel. So it's made up of a silicon steel that is fully laminated. The number of stampings are stamped together to form the stator. Like a paper, n number of stampings available. All these stampings are laminated and compressed, pressed together to form the stator. It's not a single piece. N number of thin sheets available that are combined together to form the stator. Laminated silicon steel stamping minimize the eddy current loss. So why we are going for lamination and why we are going for stamping means in order to reduce the eddy current loss. The stator core consists of three-phase winding connected in either star or delta are called a stator winding. So the stator core having the winding connected in either in star connection or delta connection, that is called a stator winding. The stator winding is excited by the three-phase supply to produce the rotating magnetic field. So the stator winding is connected to the three-phase supply. So it will produce the rotating magnetic field. Rotor is placed inside the stator. Just now we discussed the diagram. The rotor is available inside. So it is laminated and slots on the outer periphery to carry the rotor winding or rotor conductors. So this rotor also having the slots that are also laminated and also having the slot. In that slot the rotor winding or rotor conductors are placed. So it is made up of a cast iron. There are two types of rotor construction available. The rotor, there are two types. One is the screw gauge rotor, another one slip ring induction motor or phase wound rotor. So this screw gauge means the copper bars are available. Slip ring means the separate winding is available. That is a major difference. So this one can be modified. This windings are this is permanent. The copper bars are permanently placed in the rotor. So that there are majorly two types, screw gauge rotor slip ring induction motor or phase wound rotor. First we will see the squirrel cage rotor. So this is a rotor. So this is nothing but a copper bar. These lines are nothing but copper bar. Copper bars are permanently placed. So that will act as a copper winding or act as a rotor winding or rotor conductor. So we cannot modify. During the construction itself, the copper bars are permanently placed. But in case of slip ring, we can add some external resistance. We can modify the winding also. But this is permanently placed. So there is no modification can be done in this type squirrel cage rotor. Now we'll see the construction. It consists of cylindrical laminated core. So this is cylindrical. It's like a cylindrical laminated core with slots to place the rotor conductor, which are nearly parallel to the shaft axis or skewed. Skewed means slightly it is having the inclination. It's not a straight line, inclined. Right. So there are lot of advantage available to place the rotor conductors in a skewed manner. Right. So here it is the laminated core, slots are available in the rotor conductors are placed in a skewed manner. The rotor conductors are not wires, but the bar of copper or aluminum or alloy. This is not a wire. The copper bars are permanently placed in the slots. One bar is placed in each slot. Each slot having one bar. At the end of the rotor bar conductors and short circuited by heavy end rings. So all the copper bars are short circuited by using the end ring. Since the rotor bars are permanently short circuited, it is not possible to add external resistance. So I already told in the second type we can add the external resistance. In first type the copper bars are permanently placed. So not possible to modify the resistance, not possible to add any resistance. In series with the rotor for starting purpose. During the starting, if you add the resistor, the motor will take the less current. We can reduce the starting current, but that is not possible in case of this squirrel cage rotor. So the rotor is skewed because we already told it's not a straight line, it is a skewed because there are two different purposes available. It helps the motor to run quickly with reduced noise. The noise is reduced. Reduces locking tendency of rotor. The locking between stator and rotor is reduced because of skewed. If it is placed in a straight line or normal line, there may be a possibility of locking. If this skewed means there is some phase difference will happen between stator and rotor. So that reducing the locking tendency, that is rotor teeth remains under the stator teeth due to the magnetic attraction between the two. There is we can avoid the locking of between the stator and rotor. Now we'll go to the second type, slip ring rotor or phase wound rotor. So in the slip ring rotor or phase wound rotor, separate windings are available for the rotor. So this is the stator. Consider this is the stator. 3-phase supply is given to the stator. So we have the rotor available here. Rotor is available. That also it is connected in a star connected. So that is connected to the slip ring. So these are the windings. The brushes are available. Through the brushes the supply is given to the rotor windings. Right. So this is shaft. Shaft is available. So this shaded portion is the brush. This portion is nothing but a slip ring. Right. So the windings are placed in a rotor. In a previous case, the copper bar or aluminum or alloy bar available permanently. But here the windings are placed. The supply to the winding is given through the slip ring and brushes. So the other end we can easily add the resistor. So this is the external resistance. Right. So it is in a maximum resistance position. The resistance is maximum, so that current taken by the motor is very lesser. Thereafter we can slowly reduce the resistor so that the current increases gradually, so that voltage and speed also increases gradually. So it is possible to add the external resistance in this type, slip ring rotor or phase wound rotor. This external resistor are used to limit the starting current. That is the main purpose. So this facility available in the slip ring or phase wound rotor, that is not possible in the squirrel cage rotor. Now we'll see the description. So it is in this rotor winding is similar to the stator. Stator and rotor windings are similar. Rotor carries three-phase star or delta connected winding. Either star connected or delta connected windings are available. These windings are placed in slot in rotor, is placed in the slot. One end of all windings are connected to the common place. The other end of three-phase windings are brought out and connected to the slip ring mounted on the shaft with the brush on them. So one end is connected commonly, another end is connected through the slip ring and brushes. So that is available here. So this is a three-phase winding, star connected winding. In this diagram, star connected windings are available. So the one end is connected commonly. One end of all three phases are connected. So this is the common point. The other end is connected to through the brush and slip ring. Okay, that is given here. One end is connected commonly, another end is connected through the brush and the slip ring. These brushes are then externally connected to the three-phase star connected rheostat. The external resistance are connected, and other end is connected through the rheostat. Why we are connecting this rheostat? The use of brush, slip ring and external resistor is to increase the starting torque and decrease the starting current. While adding the resistance, we can increase the torque, because initially the starting torque will be more, right? This purely depends upon the resistance value. When the resistance is more, the torque also more, and reduce the starting current. So by slowly decreasing the resistor value, we can slowly increase the voltage applied and current taken, so that it is possible to go for a speed control of the motor, right? Initially the resistor is in the maximum resistance position, so the current taken is very lesser. By slowly reducing the resistance, we can increase the current applied to the current taken by the motor, voltage applied to the motor, so that we can control the speed of the motor. Now we will compare this screw gauge rotor and slip ring or phase wound rotor. The comparison we will see the comparison. So here we will see the screw gauge rotor and slip ring or phase wound rotor. So in the screw gauge rotor, the rotor consists of bar of copper bars available, but here three-phase winding is available. In slip ring we have three-phase winding. The construction is simple. During the construction itself, the copper bars are placed. There is no more alteration. But here construction is complicated, because we need to place the three-phase winding. So because of this copper bar, the resistance cannot be added. But here we can add the resistor. Externally we can add the resistor. So there is no slip ring and brush. But here, because of three-phase winding, in order to get the supply, we need a slip ring and brushes are available. Right. So due to this, the rotor is cheap. During the construction itself, the copper bars are placed. So it is cheap, but here it is costly, because we need to place the winding. The moderate starting torque here, but here high starting torque. Why? Initially we added the resistor, so the torque is proportional to resistance value. Initially the resistor is very high, so that we get the high starting torque. So due to this starting torque and external resistors available here, but is not available here, speed control is not possible by adding the external rheostat, since the rotor is short circuited. The main advantage is here is we can go for a speed control by adding the external rheostat is possible. That is not possible in the screw gauge rotor. Rotor copper loss is less, and so that high efficiency. So because here there is no copper winding, copper bars only available. So automatically the loss due to the copper is lesser, so that we can get the more efficiency. But this rotor's copper loss is more, because the copper winding is available. Here copper bars are available. So we will get the less efficiency compared to the screw gauge rotor. So it is mainly used in the lathe, drilling, fan, blower, water pump, grinder and printing machines, where we need the moderate torque is required. This one having high starting torque, so used in the lift and hoist. So these two are, and crane, this and elevator, compressor, these are all started with the loaded condition. So we need definitely we need the high starting torque. Lift means already the passengers are available. So lift hoist means the load is available. So for that case we are using this slip ring slip ring or phase wound rotor having the high starting torque. So in this video we discuss about the construction of three phase induction motor, stator and rotor. Main part is stator and rotor. The rotor again having two types, squirrel cage rotor and slip ring rotor. The construction we discuss, and also we discuss the comparison between squirrel cage and slip ring rotor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Viewers, in this video we will see the principle of operation three phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, three phase induction motor working principle. It works on the principle of electromagnetic induction. When a three phase supply is given to the three phase stator winding, rotating magnetic flux RMF is produced. So it is based on the electromagnetic induction. The rotating magnetic field is produced in the stator while giving the supply. Now we will refer the diagram. So this is the stator available. This is the rotor conductors. So initially we are giving the supply to the stator winding. So due to that, the rotating magnetic flux, the fluxes keep on changing because of three phase AC supply. The voltage level keep on changes. So the flux produced in the stator due to the three phase winding, that also keep on changing. That is called a rotating magnetic flux. Initially these rotor conductors are in a stationary position. It's not rotating, stationary position. So this magnetic flux is linked with the stationary conductors. So what will happen when a conductor cuts the magnetic flux and EMF is induced, right? Based on the principle, this magnetic flux cut the conductors. Initially this conductor is a stationary, there no current is flowing in the rotor conductors. This magnetic flux will cut these conductors. So when a conductor cuts the magnetic flux, what will happen? The EMF is induced in the rotor conductors. These rotor conductors are in a closed circuit, so the current will start flowing through the rotor conductors. So refer this diagram. So this dotted line is indicate the direction of current in the rotor. Initially there is no current. So after the interaction with the magnetic flux, EMF is produced. This EMF will circulate the current in the rotor because of closed circuit, that is indicated in this diagram. Now what will happen? This rotor conductor become a current carrying conductor. Initially stationary conductors, because of interaction of the flux, the current is flowing. So it is a current carrying conductor. When a current carrying conductor placed in a magnetic field, due to the law of interaction, when a current carrying conductor placed in the magnetic, what will happen? It experiences a force. So that is given in the third diagram. So this is the flux direction. This is the direction of the force, right? When a current carrying conductor placed in the magnetic field, it experiences a force. So all conductors are connected together. So the force by the all conductor will tends to rotate the rotor. The rotor starts rotating, right? So this is the basic principle of the induction motor. Initially the supply is given to the stator, so the rotating magnetic flux is produced. This flux cut the rotor conductors. Due to that, EMF is produced. That EMF will circulate the current. Now the current carrying conductor placed in the magnetic field, due to this it will experience a force, so it will start rotates, right? So this is the basic principle. Now we'll see the description. We'll see what is the speed of the rotor and other things. The speed of the rotating magnetic field is synchronous speed, ns, right? The speed of the stator is the nothing but synchronous speed. How will calculate the synchronous speed? Ns equal to 120 f by p. All are constant. Frequency is constant and number of pole is constant. So from that we can find the synchronous speed. Synchronous speed means the speed at which the motor is designed, right? It is based on the supply frequency and number of poles. Let the direction of rotating magnetic field is in clockwise direction. We'll consider clockwise direction, right? Now the rotor is stationary. Stator magnetic field is revolving at a speed of ns. This revolving field cut the stationary rotor conductors. When a conductor cuts the magnetic flux, an EMF is induced in the conductor. When there is a closed path, current start flowing to the EMF, right? So initially the rotor is stationary. This rotor conductor cut the magnetic flux, so that EMF is induced. That EMF will circulate the current because of closed circuit. Now what will happen? Now we have current carrying conductor placed in the magnetic field. By law of interaction, when a current carrying conductor placed in a magnetic field, the conductor experiences a force. Hence all the conductor experience a force which together give a torque which tends to rotate the rotor. So due to the experiencing the force, all the conductors are having the together connected together, so it will start to rotate with the required torque. The direction of force is same as that of rotating magnetic field. Hence the rotor start rotating in the same direction as the magnetic field. The rotation of the rotor and rotation of the rotating magnetic field in the stator both are in same direction. Now we'll see the speed of the rotor as well as the speed of the stator. This is a very important thing. Ns is the speed of rotating magnetic field in RPM. That is the speed of the rotating magnetic field. But N is the speed of the rotor. This is the actual speed of the motor. This is the speed at which the motor is designed. This N is the speed of the rotor or actual speed of the motor. The difference ns minus n is nothing but relative speed between the two, between the stator and rotor, ns minus n. The rotor always rotate in the same direction as that of rotating magnetic field, right? Ns minus n is the relative speed. Now we'll see analyze that what will happen if ns equal to n. Ns is the synchronous speed and n is the actual speed. If both are equal, whether it is possible to have the synchronous speed and speed of the rotor. When the rotor rotates it, try to catch the speed of the rotating magnetic field. The rotor will try to catch. If it is catches the speed of rotating magnetic field, then the relative motion of the is 0. That is ns minus n. Both are equal means it becomes 0. Therefore, the relative motion in the main cause for EMF is also 0. Because if both are equal mean, both of equal speed mean the relative speed is 0. So the relative motion, that is the important cause for EMF, is also 0. So the rotor flux required to produce torque is also 0. Therefore the rotor will not rotate. If both are equal, what will happen? The relative speed becomes 0, EMF becomes 0, so the torque produced also 0, the motor will not rotate. So the induction motor never runs at the synchronous speed. That is the important thing. The induction motor never runs at the synchronous speed. The speed at which the motor rotates is called a subsynchronous speed. It is always subsynchronous speed. Or otherwise, it is due to that it is called a asynchronous motor. We have synchronous motor available, always rotating in the synchronous speed. But this induction motor never run at the synchronous speed. So that is called a asynchronous motor. If it is rotated at synchronous speed, what will happen? The rotor will not rotate due to the relative motion is 0. So in this video, we discuss about the working principle of three-phase induction motor based on the rotating magnetic field of the stator, then the rotation of the rotor. If both are equal, what will happen? That also discussed. Finally, we see that it is a asynchronous motor. Subscribe this channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the slip of induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, slip of induction motor. Now we'll see the speed of the stator. is nothing but a speed of rotating magnetic field or synchronous speed equal to ns. This ns is nothing but synchronous speed. The motor designed at the time of designing, the speed is the ns. Also it is called a speed of the stator or speed of the rotating magnetic field. But the actual speed of the motor or rotor, speed of the rotor is n. The difference between these two, n and ns, is nothing but a slip of the induction motor. So the slip is measure of difference between the synchronous speed and its shaft speed. The difference between these two is nothing but a slip of induction motor. So based on that we can calculate the slip speed. ns minus n is nothing but a slip speed. The speed slipped is nothing but difference between synchronous speed and the speed of the rotor. So that is the difference between the speed of the rotating magnetic field and that of rotor is called a slip speed. Now we will see the definition of the slip. The slip is also called as a absolute slip or fractional slip. The another name is absolute slip or fractional slip. So that is the difference between the synchronous speed and actual speed of the rotor, ns and n, expressed as a fraction of synchronous speed is called a slip of the motor. That is ns minus n divided by ns. Right? The difference between synchronous speed and speed of the rotor expressed in terms of synchronous speed ns is nothing but a slip of the induction motor. While taking percentage of slip, ns minus n divided by ns into 100. We need to multiply with 100. Now we will see the speed of the motor in terms of the slip. The speed expressed in terms of slip. We know that s equal to ns minus n divided by ns. So cross multiply this. So s into ns equal to ns minus n. Right? Bring this n in the left hand side, s ns in the right hand side. So while coming this side, this minus n become plus n. This s into ns become minus s into ns. The ns available commonly, take ns outside, so that n equal to ns into 1 minus s. So the speed of the motor in terms of synchronous speed and slip is n equal to ns into 1 minus s. Now we will see the slip at the various stages, starting and running condition. Slip at the starting condition. We will see the what is the slip at the starting condition. So at the time of start, the speed of the motor is 0. So at the beginning, it is that there is no speed, so n equal to 0. The definition of slip is s equal to ns minus n divided by ns. Now the n is 0. N is 0, so it becomes ns by n. So that is equal to 1. So s equal to 1. So at the beginning, at the starting condition, the slip of the induction motor is 1. So this is the maximum value of the slip, and that is occurred at the starting condition. So this s equal to 1 is the maximum value that will occur in the starting condition. When s equal to 0, what will happen? When s equal to 0, ns equal to n, because we know the formula n equal to ns into 1 minus s. If s equal to 0 means 1 minus 0 is 1, so n equal to ns. Synchronous speed and speed of the rotor both are equal, but ns equal to n is not possible for induction motor. So that slip of the motor cannot be 0 at any case, right? So this ns minus n is not possible. If synchronous speed and rotor speed is equal, then the rotor will be locked. The rotor will not rotate, right? So the slip cannot be a 0 value, right? So at the any case, the slip is not 0. So it is greater than 0, and also it is maximum of s equal to 1. The minimum value is greater than 0, maximum value is 1. Now we will see the effect of the slip on the rotor parameters. Various rotor parameters, what will happen due to the slip. Let us study the effect of slip on the following rotor parameters. We are going to study the 5 parameters. Due to the slip, what is the effect of the slip on rotor frequency, magnitude of rotor induced EMF, rotor reactance, power factor, rotor power factor, and rotor current. We are going to analyze the effect of the slip based on these 5 parameters of the rotor. First we will see the slip of the frequency, effect of slip of on frequency of the rotor current. Right. So when the rotor is stationary, the frequency of the rotor current equal to supply frequency. Both are equal. At the stationary condition, the supply frequency and rotor current frequency are equal. When rotor is rotating, the frequency of the rotor current will depends upon the slip of the speed, slip speed. So when the motor rotates, the speed decreases. So the frequency of the rotor current depends upon the slip speed. That is called as Fr. We will take Fr. F is the supply frequency. Fr is the frequency of the rotor under running condition. Frequency of rotor current at running condition. Now we will analyze this. So we know that the synchronous speed ns equal to 120 f by p, standard formula is available, right. So ns minus n, the difference between the synchronous speed and rotor speed equal to 120 fr by f, fr by p, the rotor. This is the frequency of the supply, this is the frequency of the rotor current. So at that time there is a difference in the speed, ns minus n, difference between ns, the synchronous speed and normal speed. Now from these two equation, we will go for this take this is equation 1 and equation 2. We will go for equation 2 divided by equation 1, ns minus n divided by ns, right. So the ns minus n is 120 fr by p, this ns is nothing but 120 f by p, right. This is rotor current frequency, this supply frequency. 120 got cancelled, this p also got cancelled. So what we got, ns minus n divided by ns equal to Fr divided by F, rotor current frequency divided by supply frequency. So we know that ns minus n by ns is nothing but a slip of the induction motor, S, right. So that S equal to Fr into F, right. Bring this F in this side, so that Fr equal to S into F. So the frequency of the rotor current is nothing but slip into supply frequency, right. So during the starting condition both are equal, supply frequency and rotor frequency is equal. During running condition it is depends upon the slip of the induction motor, so that Fr equal to S into F, frequency of rotor current, Fr equal to S into F. Now we will see the induced EMF, effect of slip on rotor induced EMF. Again we will start with the stationary. When the rotor is stationary, S equal to 1. So at stationary condition, relative speed is maximum, EMF induced is maximum, and the proportional synchronous speed is also proportional to ns. E2 is directly proportional to ns. E2 is nothing but EMF induced in the rotor when it is stationary, right. So during stationary condition, S equal to 1, speed is maximum, induced EMF also maximum, that is depends upon the synchronous speed. E2 is directly proportional to N2, right. E2 is nothing but EMF induced in the rotor during the stationary condition. So at the running condition what will happen, as rotor start rotating, relative speed between the rotating magnetic field and rotor decreases, and hence EMF also decreases, and it is proportional to the relative speed ns minus n. So at the beginning it is both are equal, so it is proportional to ns. When it is start rotating, there is a difference between the relative speed and speed of the rotor, so the induced EMF is depends upon ns minus n. So that E2R is directly proportional to ns minus n. E2 means rotor EMF induced in the rotor under starting condition. E2R refers EMF induced in the rotor under the running condition, that is depends upon difference in the speed, right. So that is given, rotor induced EMF at the running condition, right. Now we will go for the ratio E2R divided by E2. E2R is ns minus n, E2 is ns. We are going to divide the two equations, above two equations, right. So this ns minus n by ns is nothing but a slip of the induction motor, yes, we know that. So that E2R divided by E2 equal to S. So cross multiply this, so E2R equal to S into E2. So the rotor induced EMF under running condition is depends upon the slip of the induction motor, right. Thus during starting condition both are equal, E2R is directly proportional to N2. Now it is depends upon the slip of the induction motor. Now we will see the effect of slip on rotor resistance and reactance R and X. So the rotor winding has its own value of resistance and reactance. Now again we will start with the starting condition. At the starting condition, standstill condition, N equal to 0. We will take this R2 is rotor resistance per phase. X2 is the rotor reactance per phase. Right. So at the standstill, FR equal to F. Both are equal. Supply frequency and rotor current frequency both are equal. Right. So if L2 is the impedance of the rotor, so we can write X2 equal to 2 pi F into L2 ohm per phase. So general formula, reactance X equal to 2 pi FL. So in that we are taking L2 is the impedance of the rotor, right? L1 refers stator, L2 refers the rotor, right? So under starting condition N is 0, so the reactance is X2 equal to 2 pi FL2. This R2 as it is, we can take as it is. Now we will go for a running condition. So under the running condition, FR equal to S into F, that we already discussed. The frequency of the rotor under running condition is slip into F. So X2R equal to 2 pi FR into L2. So this is X2 is the reactance under standstill condition. X2R means under running condition. So that is F2 pi. This F also now replaced by FR under running condition into L2. But this FR is nothing but S into F. So 2 pi FR is replaced by S into F L2. So that is nothing but S into 2 pi FL2. This 2 pi FL2 is nothing but the X2. So S into X2. So the reactance of the rotor under running condition is depends upon the slip of the induction motor, S into X2, right. So this X2R is the rotor reactance at running condition. Rotor reactance is same at standstill and at running condition. The resistance value is same. It is not depends upon the slip. Resistance value is same for both standstill as well as running condition. Now we will go to the impedance. So the rotor impedance at standstill is very simple. Z2 equal to R2 plus JX2. Resistance and reactance. So while taking magnitude, it is square root of R2 square plus X2 square under the standstill condition. But in case of running condition, Z2R, Z2 refers starting condition, Z2R means under running condition. So that R2 plus JX2R, R2 is same for standstill as well as running condition, but the impedance, but the reactance will be X2R. It become X2R. This is a starting condition, this is running condition. So while taking magnitude, it is square root of R2 square plus X2R square. X2R is nothing but S into X2. Just now we discussed. So replace this X2R by SX2. So this is the impedance under the running condition. So this depends upon the slip of the induction motor. Now we will see the rotor current, effect of slip on the rotor current. Let us take I2 is the rotor current per phase at standstill. I1 refers the stator current. I2 means is a rotor current. E2 EMF per phase at standstill. Z2 impedance per phase at standstill. Right? We already discussed E2 and Z2. Right? So that we will go for I2. I2 is E2 divided by Z2. So that E2 divided by square root of R2 square into plus X2 square. Right? This is for under the standstill condition. Somehow same thing will go for a running condition. I2R. I2 means starting condition. I2R refers rotor current per phase at running condition. Similarly, E2R is nothing but S into E2, that already we discussed. Right? So the EMF per phase at running condition. So that Z2R equal to R2 square plus S into X2. Previously we have only X2. Now it is S into X2, right? So these two things are we already discussed, the details about I2 and E2. Now we got the impedance. From that we can easily calculate the rotor current. I2R equal to E2R divided by Z2R. right? So the E2R is S into E2. Z2R is now just now we calculated square root of R2 square plus X into X to the whole square. So this rotor current under the running condition is depends upon slip of the induction motor. Now we'll go to the power factor, effect of slip on the power factor. Now consider this impedance triangle, the angle pi 2 is there, the resistance is a reference. In this with the 90 degree we have the reactance. The vector sum of these two is the impedance. So general impedance diagram, resistance, reactance and impedance. So at the standstill condition, this cos pi 2, this cos pi is nothing but a power factor. So cos pi 2 means this is opposite side, this is adjacent side, this is hypotenuse. So the cos means adjacent side by hypotenuse, R2 divided by Z2, right? The general formula available, R2 divided by Z2, right? So R2 divided by Z2 is nothing but R2 square plus X2 square, general formula under standstill condition. The same thing under the running condition mean we need to add the slip of the induction motor. Same formula only, R2 divided by Z2R. This R refers the running condition. The resistor value is same for both running condition as well as starting condition, right? So Z2R is nothing but R2 square plus S into X2 square, right? So this is a formula for power factor under standstill condition. This is for under running condition. During running condition it is depends upon the slip of the induction motor. So in this video we discuss about the slip of the induction motor, definition and the formula, and effect of the slip on rotor parameters. 5 parameters we discussed. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the slip of 3-phase induction motor part 1. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the first problem. A slip ring induction motor runs at 290 rpm at full load when connected to a 50 Hz supply. Determine the number of pole and slip. Synchronous speed is 300 rpm. So first we will analyze the data. The synchronous speed is given as 300 rpm. But the motor rotates at 290 rpm at the full load. The frequency is 50 Hz. We need to find the number of poles and slip of the induction motor. First we will find the synchronous speed. The formula for synchronous speed is ns equal to 120 f by p. So in this synchronous speed is given, frequency also given, so that we can easily calculate the number of poles. So by interchanging these two parameters, p equal to 120 f divided by ns. This p is brought to numerator, n is brought to the denominator, so that we got the expression for pole 120 f by p. So that is equal to 120 into the frequency is 50, the synchronous speed is 300. So by simplifying this we got p equal to 20, number of poles equal to 20. Now we'll go to the slip of the induction motor. The slip of the induction motor, the formula S equal to ns minus n divided by ns. That is the difference between the synchronous speed and the rotor speed divided by synchronous speed, right? So the synchronous speed is given as 300. The speed at of the rotor at full load is 290. So 300 minus 290 divided by ns, 300. So by simplifying this, what we got, 0.0333. So while getting the percentage, it is around 3.33 percentage. So we calculated number of poles as well as slip of the induction motor. Now we'll go to the second problem. A 12 pole 3-phase alternator driven at 500 rpm supplies power to 8 pole 3-phase induction motor, right? So the 8 pole 3-phase induction motor is available. It is driven by the 12 pole 3-phase alternator, which is rotating at a speed of 500 rpm. if the slip of motor at full load is 3%, the slip of the induction motor is given. Calculate the full load speed of the motor. We need to find the full load speed. Now we will analyze the data. For the alternator, the number of pole is 12, speed is 500 rpm. For induction motor, the number of poles equal to 8, the slip is 3%. 3% mean 0.03. We need to find the speed of the motor. First we will find the frequency of the induction motor from the alternator data. That n equal to 120 f by p, that's a standard formula available, speed equal to 120 f by p. From that we can find the frequency value. This n and p is multiplied and 120 is brought in the denominator, so that f equal to p into n divided by 120, number of poles and speed divided by 120. This data refers the alternator. Alternator, number of poles and speed is refer the alternator, so that we can get the frequency of the supply. So the number of poles of alternator is 12, the speed is 500 rpm divided by 120. So 12 into 500 divided by 120, it gives 50 Hz. So the supply given to the induction motor is having 50 Hz. Now we can find the synchronous speed, ns. Our final aim is to find the full load speed. Before that we will find the synchronous speed. ns equal to 120 f by p, same formula, but this one refers the induction motor. This one refers the alternator. Now this one refers the induction motor. So ns equal to 120 f by p, that is equal to 120 into frequency. Frequency just now we calculated 50 Hz divided by number of pole is 8 pole. For induction motor, 3-phase induction motor, number of pole is 8. So by simplifying this, what we got, 750 rpm. The synchronous speed of the induction motor is 750 rpm. So by using the data, we can able to find the full load speed. Full load speed in terms of slip is available, this formula, n equal to ns into 1 minus s, because slip is already given, ns also calculated. So by using this formula, we can able to calculate the full load speed of the 3-phase induction motor. So n equal to ns into 1 minus s. ns is 750, just now we calculated, into 1 minus the slip is given 3%, that is 0.03. So by simplifying this, we got n equal to 727.5 rpm. So we calculated the full load speed of the 3-phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the solved problem based on the slip of the 3-phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the first problem. A 3-phase induction motor is wound for 4 pole and is supplied from a 50 Hz subsystem. Calculate the synchronous speed, rotor speed when the slip is 4%, rotor frequency when the rotor runs at 600 rpm. Now we will analyze the given data. The number of poles is given as 4. Number of pole equal to P equal to 4. The supply frequency given as 50 Hz. So first we need to find the synchronous speed and speed of the rotor at 4% of the slip. Then rotor frequency. First we will see the synchronous speed. Synchronous speed ns equal to 120 f by p. Very standard formula available for a synchronous speed. So the number of poles and frequency is given, so that by using this formula we can able to find the synchronous speed. So 120 f by p, that is equal to 120 into the frequency is 50 Hz divided by number of poles equal to 4, right. So by simplifying this, what we got, 1500 rpm. So the synchronous speed of the 3-phase induction motor for the given data is 1500 rpm. Next we will find the rotor speed at 4% of slip. 4% of slip means 0.04. Slip value is 0.04, right. So the rotor speed can be calculated from this formula, n equal to ns into 1 minus s. this formula relating the synchronous speed and slip. From synchronous speed and slip, we can able to find the rotor speed. So these two data are available. So by using the formula, we can able to find the rotor speed. So ns is 1500. Now just now we calculated into 1 minus the slip is 0.04. So 1500 into 1 minus 0.04. By simplifying this, we got 1440 rpm. So the synchronous speed is 1500. Because of the slip, the motor rotates at 1440 rpm. Now we'll find the rotor frequency for a given speed of 600 rpm. For a given speed of 600 rpm, we need to find the rotor frequency. First, we will find the slip at 600 rpm. If the speed is 600 rpm, what is the slip? The general formula is S equal to ns minus n divided by ns. The difference between synchronous speed and rotor speed divided by synchronous speed will give the value of slip. So the synchronous speed is 1500. That's now we calculated. The speed is given as 600 rpm. So 1500 minus 600 divided by 1500. So it is about 0.6. The slip is 0.6. For the given 600 rpm, the slip of induction motor is 0.6. So with this data, we can able to find the rotor frequency. Fr. F refers the frequency of the supply system. Fr refers the frequency of the rotor. The formula available, Fr equal to S into F. Slip into frequency. The slip is what we calculated 0.6. So 0.6 into 50. The frequency is 50. So 0.6 into 50, it gives 30 Hz. So the frequency of the rotor is 30 Hz. So now we calculated all three parameters: synchronous speed, rotor speed at 4% of slip, and rotor frequency at the speed of 600 rpm. Now we'll go to the second problem. An 8-pole 3-phase induction motor is supplied from 50 Hz AC supply. On full load, the frequency of induced EMF in rotor is 2 Hz. Find the full load slip and corresponding speed. So first we will analyze the data. The number of poles is given, P equal to 8. The frequency of the supply is 50 Hz. And the rotor frequency is given 2 Hz. We need to find the slip of the induction motor for that corresponding speed of the induction motor. First we will find the slip of the induction motor. We know that the Fr equal to S into F, because we need to find the slip. The two data available is rotor frequency available and the supply frequency is available. So by using this formula, we can easily calculate the slip of the induction motor. So Fr equal to the frequency of the rotor equal to slip into supply frequency. So from that, S equal to Fr divided by F. Rotor frequency divided by F. The rotor frequency given 2, the supply frequency is 50. So 2 divided by 50, it is 0.04. That is nothing but 4%. So for this given data, the slip of the induction motor is 4%. Now we need to find the corresponding speed, the corresponding rotor speed. Before that, we will find the synchronous speed, so that we can able to find the rotor speed. So synchronous speed ns equal to 120 F by P, very standard formula available. This F is nothing but supply frequency divided by number of poles. So 120 F by P means 120 into frequency is 50, number of poles 8. So by simplifying this, what we got, 750 rpm. The synchronous speed of the 3-phase induction motor is 750 rpm. Now we can able to calculate the rotor speed. For this, the slip is 4%, synchronous speed is 750. So by using these two data, we can able to find the rotor speed. Slip means the speed of the difference between the rotor speed and the synchronous speed. So n equal to ns into 1 minus s. The formula relating the rotor speed, synchronous speed and slip is available. So these two data are available, so we can easily calculate the speed of the rotor. So n equal to ns into 1 minus s. So n equal to ns is 750 into 1 minus s. 1 minus s is 0.04, 4%. Right? So by simplifying this, what we got? 720 rpm. So the synchronous speed is 750. Because of 4% of slip, the speed reduced to 720 rpm. So in this problem, we calculated the slip and the corresponding rotor speed. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the slip of the 3-phase induction motor part 3. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the problem. For a 4-pole 3-phase 50 Hz induction motor, the ratio of stator to rotor turns is 2. On a certain load, its speed is observed to be 1455 rpm when it is connected to a 415 voltage supply. Calculate. The first one is frequency of rotor EMF in running condition, magnitude of rotor EMF at standstill, magnitude of rotor EMF at running condition. Assume a star connected stator. So first we will analyze the given data. So what are the data available? So the number of poles is given 4. Number of poles is 4. The frequency of the supply is given 50 Hz. Then ratio between number of turns, ratio between stator to rotor is 2. 2 is given as a ratio between the stator and rotor turns. The speed is 1445 rpm. The speed of the 3-phase induction motor is 1445 rpm. The voltage given V1, V1 refers to stator, V1 equal to E1 equal to 415 voltage. In order to find the E1 per phase is 415 divided by root 3, it is 239.6 voltage. It's a line voltage, this one phase voltage. First we need to find the frequency of the rotor EMF in running condition. There are two conditions available, running condition and starting condition, standstill. Right. First we need to find rotor EMF and the running condition. First we will find the synchronous speed of the induction motor, synchronous speed, Ns equal to 120 F by P, very standard formula available. Right. The frequency and number of poles is given in the problem, so that you can easily calculate the synchronous speed. So Ns equal to 120 F by P, that is equal to 120 into frequency is 50, number of poles equal to 4. So by simplifying this, we got 1500 rpm. Right, the motor synchronous speed of this 3-phase induction motor is 1500 rpm. Now we will calculate the slip, because the running condition, in order to find the running condition, we need the value of slip. The formula for slip is Ns minus N divided by Ns, difference between synchronous speed and rotor speed divided by synchronous speed. Right. So this rotor speed is given in the problem, 1445 rpm. Synchronous speed is now calculated. So Ns minus N divided by Ns, 1500 minus 1440 divided by 1440, it gives 0.03. The slip is 0.03. Right. So synchronous speed is 1500, it is rotating at 1440. So based on that, we got the slip of the induction motor is 0.03. From this slip of the induction motor, we can easily able to calculate the rotor speed. So the rotor speed is rotor frequency, Fr equal to S into F. Because of running condition, we need to find the frequency by using this slip of the induction motor. So this F is the frequency of the supply, S is slip. By using this S into F, we will get the frequency of the rotor. So Fr equal to S into F. S is 0.03, the slip is 0.03, just now we calculated, and the frequency is 50 Hz. So by simplifying this, we got 1.5 Hz. The frequency of the rotor under running condition is 1.5 Hz. Now we will find the magnitude of the rotor EMF at the stand. So at standstill, this E2 divided by E1 equal to N2 divided by N1. Standstill mean at the starting. Previously what we discussed, running condition. E2 divided by E1 equal to N2 divided by N1. That is, this 2 refers the rotor, 1 refers the stator, E refers the EMF, N refers the number of turns. It is very similar to transformer. 3-phase induction motor is also called as a rotating transformer. Right? So, based on that we are using this formula. So, E2 divided by E1 equal to, we can write 1 by 2 because N1 by N2, the ratio of stator to rotor turns is given 2. Right? So, N1 by N2 is 2 means N2 by N1 by, we can interchange, we take the reciprocal, so that is 1 by 2. So, we can replace this N2 by N1 equal to 1 by 2. So, this 1 by 2 means 0.5. E2 divided by E1 equal to 0.5. So, from this ratio we calculated 0.5. So, cross multiply this so that E2 equal to 0.5 into E1. 0.5 into E1 is already calculated, phase value 239.6. Already the line value is given, from that we calculated the phase value. Right. So, 0.5 into 239.6. So, by simplifying this, what we got? 119.8 voltage. So, the magnitude of rotor EMF under the running condition is 119.8 voltage. Now, we will find the magnitude of rotor EMF at the running condition. This one is a standstill condition. Now, we will go for running condition. The running condition very simple, E2R equal to S into E2. So, the E2 refers standstill. This E2R refers means running condition. During running condition, we need to take into account of slip of the induction motor because the speed decreases. That is expressed in terms of slip. So, the E2 phase is available under standstill. So, the E2 under the running condition can be easily calculated from this formula, E2R equal to S into E2. So, S is given as 0.03, 3% into E2, under standstill we calculated 119.8. So, by multiplying this we got 3.594 voltage. The magnitude of the rotor EMF under the running condition is 3.594. Now, we calculated all the parameters: frequency of the rotor under the running condition, magnitude of rotor EMF under the standstill condition and running condition. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the solved problem based on the slip of the 3-phase induction motor part 4. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the problem. A 3-phase 4-pole 50 Hz induction motor has slip ring rotor. So, this coming under the slip ring rotor. The rotor winding is star connected with 0.2 ohm of resistance per phase and standstill reactance of 1 ohm per phase. Its open circuit EMF between slip ring is 120 voltage. When stator is excited by the rated voltage, its full load speed is 1440 rpm. Find the rotor current at and rotor power factor at starting as well as full load. We need to find the two parameters, rotor current at the corresponding rotor power factor for starting condition as well as the full load condition. Now, we will analyze the data. What are the data available in this given problem? The number of poles is 4. Poles is given as 4. The frequency of the supply system is 50 Hz. R2 and X2. This R2 refers rotor, R1 refers stator. The rotor data are given. Resistance is 0.2 ohm and reactance, standstill reactance is 1 ohm. And E2 is given 120 voltage. This E2 also refers the rotor, 120 voltage, line voltage. In case of phase voltage, this 120 divided by root 3, 69.282 voltage. And the speed is given 1440 rpm. Now, we need to find the rotor current during the starting as well as full load. During starting, we can use the normal formula. During the full load, we need to consider the slip of the induction motor. Now we'll find the rotor current at the starting condition. So I2 equal to E2 divided by Z2, the general formula. The current equal to voltage divided by impedance. That is E2 divided by impedance is the sum of resistance and reactance. Reactance of the rotor. 2 refers rotor. So the rotor voltage divided by rotor impedance R2 plus JX2. So this R2 plus JX2 is written as square root of R2 square plus X2 square magnitude. Right. So all these data are available. E2 is 69.282. E2 given us 120 voltage line voltage, this one phase voltage, and the resistor value given 0.2 ohm, reactance given as 1 ohm. So all the data are available. So by simplifying this, what we got, 67.934 ampere. The rotor current at the starting is 67.934 ampere. Now we will find the rotor current at the full load condition. For a full load means definitely we need the value of slip of the induction motor. So in order to find the slip of the induction motor, first we will find the synchronous speed. Synchronous speed equal Ns equal to 120 F by P, very standard formula. Number of 120 into frequency divided by number of poles. These two data are available. 120 into the frequency given 50, number of poles is 4. So 120 into 50 divided by 4, what we got, 1500 RPM. So the synchronous speed of the induction motor is 1500 RPM. So from this we can able to find the slip of the induction motor. S equal to Ns minus N divided by Ns. Synchronous speed minus rotor speed divided by synchronous speed. See, the speed is N is already given, 1440. Synchronous speed we calculated. So 1500 minus 1440 divided by 1500, it is 0.04. The slip of the induction motor is 0.04, that is 4%. Right? For a full load, definitely we need the value of slip of the induction motor. Then only we can find the full load parameters. So I2R equal to E2R divided by Z2R. Previously I2 equal to E2 by Z2. During running condition it is given I2R. R refers the running condition. E2R, EMF under the running condition. Impedance also under the running condition. How will you find E2R? E2R is nothing but S into E2. The EMF in the rotor under running condition is slip into rotor EMF under the starting condition, S into E2. Similarly, Z2R is nothing but square root of R2 square plus S into X2 square. Because R2 is constant, the reactance will vary with the slip of the induction motor. So S into X2 square. Right. So this I2 refers under the starting condition, I2R refers the running condition, that is based on this SE2 divided by square root of R2 square plus S into X2 square. So here we are referring the slip of the induction motor. Now all these data is available, we can substitute. I2R equal to 0.04 into the slip of the induction motor is 0.04 and E2 what we calculated 69.28 divided by resistance given as 0.2 and slip is 0.04 into reactance is 1. So by simplifying this we got 13.586 ampere. So the rotor current at the full load is 13.586 ampere. Now we need to find the power factor for this corresponding rotor current during starting as well as the running condition, full load condition. First we will find the rotor power factor at the starting condition. Very simple formula, cos phi 2 equal to R2 by Z2. The power factor, one simple formula is available, resistance divided by impedance, R2 divided by Z2. So R2 divided by Z2 is nothing but square root of R2 square plus X2 square, resistance plus and reactance. So that will get the impedance. So these values are already available. R2 is 0.2 square divided by the reactance is 1 square. Right. So by simplifying what we got, 0.196 power factor is cos pi 2 is 0.196 lagging. Because of the inductor we are put it as lagging. Now we will find the power factor at the full load. The full load mean we need to refer the value of the slip of the induction motor. The same formula cos pi 2r. Cos pi 2 refers the standstill condition. Cos pi 2r. R refers the running condition. R2 divided by Z2. This R2 is constant. It will not vary with the slip of the induction motor. So, it is taken as it is. But Z2 resistance plus reactance. This reactance is based on the slip of the induction motor. When the slip changes, the reactance also changes. So, S into X2. So, that is R2 divided by this R2 plus JXX2. Complex number can be written in the magnitude square root of R2 square plus S into X2 square. So, all these values are available. We can substitute the values. R2 value is 0.2, this 0.2 square plus the slip of the induction motor is 0.04 into X2 is 1 ohm. So, by simplifying this what we got 0.9805 lagging. Because of the inductor it is given as lagging. So, in this problem we calculated the rotor current under starting condition as well as running condition, then corresponding power factor at starting condition and running condition. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the torque equation of induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the topic torque equation of induction motor. The torque produced in induction motor is depends upon the following three parameters. So the torque equation also based on these three parameters. So we need to analyze these three parameters. First one, flux required to produce the EMF, electromagnetic force. So first one is the flux. What is the flux available? Next one, rotor current. It is called as I2R. I2R refers the rotor current. Then power factor of rotor circuit at running condition, that is cos pi 2R. 2R refers the rotor. So this torque is depends upon flux requirement, rotor current, power factor of the rotor circuit under running condition. So by combining three we can write it as torque is directly proportional to pi I2R into cos pi 2R. Depends upon these three parameters. Now we need to see find the expression for pi, rotor current I2R and power factor cos pi 2R, so that we can finalize the equation for torque. Now take it, this is the equation number 1. Now first we will analyze the flux produced. The flux produced in the stator is depends upon the stator applied voltage. So the pi is directly proportional to E1. Depends upon the voltage applied, the flux is produced. So the pi is directly proportional to E1. At the standstill mean that is at the rest condition, we know that E2 by E1 equal to N2 by N1, that is equal to K, transformation ratio. It is very similar to the transformer. We are treating as stator and rotor as primary winding and secondary winding. So E2 by E1 equal to N2 by N1 equal to K. I will take this E2, then EMF in the rotor, E2 by E1 equal to K. So that E1 is directly proportional to pi. So that the E1 is replaced by pi, that is equal to K, right? So the E1 is directly proportional to pi, so that E1 is replaced by pi. So by cross multiplying this, what we got? E2 equal to K into pi. This pi is multiplied here, E2 is K into pi. That is E2 is directly proportional to pi. Already we discussed E1, the pi is directly proportional to E1 and this pi also directly proportional to E2. Now we got the expression for the flux. Flux is depends upon E2. Initially it is based on E1. Based on the transformation ratio, by substituting what we got, the flux is also proportional to E2. Then we will go to the rotor current and rotor power factor. I2R. I2R is nothing but E2R divided by Z2R. EMF divided by the impedance, right? This E2R is nothing but S into E2 divided by Z2R is square root of R2 square plus S into X2 square. Rotor resistance and reactance. This formula already available, right? So E2R is S into E2. This S is nothing but the slip of the induction motor, and Z is nothing but square root of R2 square plus Sx into X2 square. We take this equation number 3. Then the power factor, rotor power factor cos pi 2R is nothing but R2 by Z2R. So this general formula is available. Power factor equal to R by Z, resistance by impedance. Based on that, we have R2 by Z2R. So that is equal to R2 divided by Z2R is nothing but R3 square plus S into X2 square into S into X2 the whole square, right? So we take this equation number 4. Now we got the expression for flux, rotor current and rotor power factor. Now we will substitute this equation 2, 3 and 4 in the equation 1, so that we can able to frame the equation for torque. So while substituting, the T is directly proportional to E2, pi. Pi is nothing but E2. This is the rotor current. S into E2 divided by square root of R2 square plus S into X2 square into this power factor R2 divided by square root of R2 square into S into X2 square. So this is available 2 times, 2 square is available, square root, so that it become easy, it become the normal term. So the E2 available 2 times, S is available, so S into E2 square into R2. This term available 2 times, so it become, while taking the square root available 2 times, so it become R2 square plus S into X2 square. So that can be written as the while equating, we need to introduce the constant K into, so that T equal to the equation for torque T equal to K into S E2 square R2 divided by R2 square plus S into X2 square. So we got the equation for the torque. Now we'll see what is the K. What is K is nothing but constant of proportionality. While equating any proportionality, we need to introduce the constant. So that the constant value is nothing but 3 divided by 2 pi ns. This ns is nothing but a synchronous speed in RPS. N divided by 60, ns divided by 60, right? So the K is nothing but 3 divided by, for 3-phase induction motor, 3 divided by 2 pi ns. Ns is nothing but a synchronous speed, that is nothing but ns divided by 60. So if we substitute the K value, we will get the final expression for the torque. T equal to 3 divided by 2 pi ns. This K is replaced. This K is replaced by this value. S E2 square R2 divided by R2 square plus S into X2 the whole square. The unit is Newton meter. So this is the equation for torque developed under the running condition. So now we got the expression for torque. Now we'll go to the equation for the starting torque. This is the normal torque under the running condition. So at the starting torque, we will analyze now what is the starting torque of the induction motor. So at the starting or instant of starting, n equal to 0. The speed is 0. So the slip S is nothing but ns minus n divided by ns. So this is the definition of the slip. So in this now n is equal to 0. N equal to 0. There is no current. There is no speed at the standstill at the starting. So this equation become ns by n. This n is 0. So ns by n got cancelled. So S equal to 1. So at the starting, the speed is 0. The speed is substituted in the slip. So we got the slip equal to 1. So in the normal torque equation is available here. The torque equation is there. In that, this S equal to 1 at the starting condition. At the starting, S equal to 1. So if you substitute S equal to 1, we will get the expression for starting torque. In this equation, we need to substitute S equal to 1. So while substituting, what will happen? This torque becomes starting torque. 3 divided by 2 pi ns, this S is 1, right? E2 into R2 divided by R2 square plus here one S will be there, that also 1. So X2 square. So this is the expression for starting torque. This S is now replaced by the 1. Now we'll see the maximum condition for maximum torque under the running condition. What is the condition for maximum torque? In order to get the maximum torque, the equation is, the condition is differentiation of torque equation with respect to slip equal to 0. D by dt of the torque equation T equal to 0. Right? We are going to differentiate the torque equation with respect to S, and if you put the by equating into 0, we will get the maximum condition. So that this is normal mathematical. In mathematics also you already studied, right? Differentiation of the term while equating 0 will get the maximum value. So here we are considering the slip. Why? The slip is variable in the torque equation, right? The torque equation, the slip is keep on changes, variable one. So we need to differentiate with respect to the variable parameter. Here the slip is the variable parameter, right? So that we are taking slip as we are differentiating with respect to the slip. So the normal torque equation is K into S E2 square R2 divided by R2 square plus S into X2 the whole square, right? So this we will go for a square this time, so that T equal to K into S E2 square R2 divided by R2 square into S square X2 square, so that it is easy for going for a differentiation. Now we need to differentiate this equation, T d by ds of T equal to 0, right? So this is a torque equation available. So d by ds, differentiation with respect to slip, into the torque equation. Now substitute this torque equation here, K into S E2 square R2 divided by R2 square plus S square X2 square, that is equal to 0. So by differentiating this equation with respect to S, equating the 0, we will get the condition for maximum torque. So we need to differentiate this expression. See, we are differentiating with respect to S, slip. The S is available in the numerator as well as the denominator, right? So the numerator and denominator available, so we can go with the U by V method. Differentiation U by V method, right? Differentiate is a division. So U by V method, what is the formula? V U dash minus U V dash divided by V square, right? So this is nothing but U. This term is nothing but U. This term is nothing but V. The numerator is U, denominator is V. So based on the formula V U dash minus U V dash divided by V square, the V. First we will write the V. So this is nothing but your V. Denominator is the V. So it is written as it is, R2 square plus S square into X2 square into U dash. What is U dash? You have to differentiate this term. U is this value, U dash means differentiate. So while differentiating, S is available. So the differentiation of S is 1. So that we got K E2 square into R2. Right. So this is U denominator value. This is U numerator value. U dash mean numerator value is differentiated, while differentiating S equal to 1 minus U. You have to write this U as it is, K S E2 square into R2 divided into V square, V dash. What is V dash? V is nothing but denominator. You have to differentiate this term. R2 square is, this is constant, so it become 0, right? This differentiation of S square is 2S into X2 square, right? So this is nothing but V dash. V is this value, V dash mean differentiate, while differentiating this is become 0. This differentiation of S square is 2S and X2 square divided by V square. This V is available, you have to write it as V square, right? Now we differentiated this equation, V U dash minus U V dash divided by V square. So this is U, this is V. So after differentiation while cross multiplying this term become 0, right? So only we got this R2 square into S square into X2 square into K E square R2 minus this entire term 2 K S square E2 square R2 into X2 square, that is equal to 0. Now we will multiply this term. Here two terms are available, so we can go for further simplification. So while multiplying here, K R2 square E cube plus, here already one E is there, so it become E cube plus k s square e2 r2 r2 into x2 square minus this term 2k s square e2 square r2 into x2, right. So this term available two times, is available two times. So 1 minus 2 means minus 1, right. This will take, this is 1, this is minus 2, 1 minus 2 is 1 minus 1. So that k r2 square into e square minus this k s square e2 square r2 into x2 equal to 0. So while multiplying this, this r2 is cube value, this e is only square, right. K r2 cube, here because here r2 square is available, here r2 is available. So r2 cube, then e2 square into this value, right. Only the small correction is there, here r2 cube e2. So again, so this value available two times, this is similar value. So 1 minus 2 is minus 1. Now we can take these terms commonly, k r2 square r2 into e2 square, these values are available commonly, k available here and here also, here r cube is available, here r2 is available, here e2 square available, here also e2 square available. So we will take the k r2 e2 square outside. So what will happen here, we have r2 square minus s square into x2 square, right. The k taken outside, s2 square is available here, e2 square is taken outside, r2 also taken outside, only we have x2 square available here, right. So this term while equating, what will happen, this term automatically 0, only we have r2 square minus s square x2 square equal to 0. Bring this term in the right hand side, so that r2 square equal to s square into x2 square. So this is r2 square, r2 square equal to s square into x2 square. Now we'll go for further simplification. So that this s square equal to r2 square divided by x2 square. So finally what we need is, we need a condition for maximum torque, so that it is expressed in terms of the slip. So while s square, while taking square root on both the side, s square become s, this term become plus or minus r2 by x2. So both the possibilities are available, plus as well as minus. Now we are neglecting the negative value, only we consider positive value, so that s equal to r2 divided by x2. So this is nothing but the value of the slip at the maximum torque. The value of the slip at the maximum torque is r2 by x2. So from that we can write the condition for maximum torque. What is the condition for maximum torque? Sm equal to r2 by x2. The slip should be equal to r2 by x2. So this is the condition for maximum torque. Now we will find the magnitude of this maximum torque. What is the max? This is the condition we calculated. Now we will find what is the magnitude of the maximum torque. So the maximum torque is obtained at Sm equal to r2 by x2. So in the torque equation, if you put s equal to Sm equal to r2 by x2, we will get the maximum, the expression for magnitude, maximum magnitude of the maximum torque, right. So in the normal torque equation is available, T equal to k into s e2 square r2 divided by r2 square plus s e2 square in e2 square. So in this s is replaced by Sm, that is equal to r2 by x2, so that we will get the maximum torque, right. So substitute s equal to Sm, that is equal to r2 by x2. So at the while substituting, the torque automatically become maximum torque, that is equal to k Sm, s is now replaced by Sm, e2 square r2 divided by r2 square into Sm square into x2 square, s become Sm square. Now we can substitute the Sm value. Sm value is nothing but r2 by x2. Here r2 square divided by x2 square. This x2 got cancelled. Now we'll go for further simplification. So after simplification, we got k e2 square r2 divided by this, take the x2 outside, so that r2 square into plus 2 r2 square. So this available two times. So k e2 square r2 square divided by x2 square into 2 r2 square. Here the 2 is not available. r2 square plus r2 square. right? So r2 square plus r2 square become 2r2 square. So this r2 square got cancelled. So what finally what we got? T maximum, the expression for the magnitude of maximum torque is k E2 square divided by 2 into x2, right? Now we can substitute this value in the torque equation, so that we will get this T max equal to k E2 square divided by 2x2. This k is nothing but 3 divided by 2 pi ns based on the 3-phase induction motor into E2 square divided by 2x2. So this is the equation for the magnitude of the maximum torque, right? By using the condition Sm equal to R2 by x2, by substituting we got the expression for the magnitude of maximum torque. Now we will see the condition for maximum starting torque. We already discussed the maximum torque. Now it is a maximum starting torque. So at the starting, the slip equal to 1. We already discussed slip equal to 1. That is Sm equal to 1 for a condition Sm equal to R2 by x2. If Sm equal to 1, what will happen? R2 by x2 equal to 1. So that R2 equal to x2. So the condition for maximum starting torque is R2 is equal to x2. The resistance of rotor and reactance of the rotor should be equal, right? So this condition we are getting by substituting S equal to 1, because at the starting slip equal to 1. By substituting this value in the condition, we got R2 equal to x2. Now we'll see the starting torque of a squirrel gauge rotor. What we discussed so far is split ring. This is squirrel gauge. In case of squirrel gauge, the resistance of squirrel gauge rotor is small than reactance. The resistance is very less compared to the reactance, and is also almost constant. Starting current I2 is of very high magnitude and lag behind the E2 by an angle of large angle, right? So the starting current is very high. So the starting torque is very poor because of current is lagging the voltage E2 at a very large angle. So the starting torque is very less. So that it is not used for motor which is used to start the heavy load. In case of the motor started with the heavy load, we are not using this squirrel gauge rotor. Squirrel gauge rotor used for only the medium load or less loaded. For heavily loaded, it is not used. So in this video, we discuss about the torque equation and condition for maximum torque, condition for maximum starting torque, and magnitude of the starting torque and starting torque of the squirrel gauge rotor. These things are discussed in the video. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the torque slip characteristics of a 3-phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the topic. Torque slip characteristics of 3-phase induction motor. The curve obtained by plotting the torque against the slip is called the torque slip characteristics of induction motor. The curve is drawn between torque and slip. Now we will see the details about what is the relation between torque and slip. When the induction motor is loaded, the speed decreases. Therefore, the slip will increases. The slip is nothing but the difference in speed between actual speed and synchronous speed. So when the motor is loaded, the actual speed of the motor decreases. So there is a difference between actual speed and synchronous speed. So that's why the slip also increases. But due to increased load, the motor must produce more torque to meet the load demand. So while loaded, speed decreases, but the motor will try to meet the required demand by producing the more torque. So the slip increases, torque also increases. So the torque depends upon the slip, right? So when it is loaded, speed decreases, torque slip increases, and same time in order to meet the load, torque also increases. So all are interrelated. So it is clear that the torque depends upon the slip. So we know that the expression for torque T equal to K into S E2 square R2 divided by R2 square plus S2 square X2 square. So, this is the expression for the torque. So, for a constant supply voltage, if the supply voltage is constant, we can take E2 will be constant. This E2 we can take it as constant. So that we can write the torque equation as T is directly proportional to S R2 divided by R2 square plus S X2 the whole square. So it is depends upon R2, X2 and slip, depends upon this parameter. When S equal to 0, the torque is also 0. So the curve starts at the 0. So the initial curve is starting at 0 value, because S is 0 mean torque also 0. Now we will go to that. There are two regions available, low slip region and high slip region. In this low slip region, when the speed of the rotor is close to the synchronous speed, that is actual speed and synchronous speed is almost nearer, mean the slip is very small. The slip is nothing but difference between the synchronous speed and actual speed. Suppose synchronous speed and actual speed is nearer, mean automatically slip is very small. So that S X2 square value is very small. S is already small, mean S X2 will be very small compared to R2 square. So we can neglect the S X2 square. In the torque equation we can neglect the S X2 square, because when the speed is low, when the speed is nearer to the rotor speed, the slip is very less. So that this slip is very less, mean S X2 square become very less. So that we can neglect, compared to R2 we can neglect this term. So this is the normal torque equation, S R2 divided by R2 square plus X X2 square. In this we are going to neglect this term S X2 square. So it become S R2 divided by R2 square. So from this it is very clear that the torque is proportional to slip. So when the slip increases, the torque also increases. So during low slip region, torque is proportional to the slip. Both are directly proportional. Now we will see the diagram. For low value of slip, torque is directly proportional to the slip. So the graph is a straight line. Both T and the torque and slip are directly proportional. So almost we will get the straight line. So we will see the diagram, this graph. So in the x axis the slip is, the data slip is given. In y axis we have torque. The graph is drawn between the slip and torque. So this is 0 value, S equal to 0, slip equal to 0. So this is the low slip region, this one high slip region. During low slip region we conclude that T is directly proportional to S. When the slip increases, torque also increases. So we are getting the straight line, right? Both are proportional. So at this point it is maximum, S equal to S sum, right? Slip corresponding to the maximum. So this is the maximum torque, T max. So this is half of the portion is almost full load torque, TFL. TFL is nothing but full load torque, right? So S equal to 0 means the torque and slip both are 0. The curve starts at 0. When the during low slip region, torque increases, slip increases, torque also increases. So we are getting the straight line. So this is the maximum point, maximum torque, and this is the corresponding to slip value. So after this what will happen? This is the high slip region. The torque decreases in a hyperbolic manner, keep on decreases. So this is the starting torque. So almost we have some value, starting torque, T start, and become 0 and reaches 0 at S equal to 1, right? So before this maximum torque, that is during low slip region, torque keep on increases and reaches the maximum value. After maximum value keep on decreases and reaches the 0 value. So beyond the maximum torque, if you load the motor, the speed decreases slowly and it will reach the 0 value and the motor will stop. So we can load up to the maximum torque. Beyond maximum torque, if the motor is loaded, what will happen? The torque decreases and becomes 0. So the motor will stop. We'll see this analysis during the high slip region, how the torque is inversely proportional. We'll see the details. We will see the details of high slip region, right? So this is the entire torque slip characteristic, low slip region and high slip region. So, we will see the analysis of this high slip region. So, during high slip region, as the load increases, the speed is decreases. While increasing the load, speed will decrease. So, the slip will increases. Speed decreases mean there is a difference between the synchronous speed and actual speed. So, that slip will increases. The torque increases and reaches the maximum value, right. So, the torque will increases, that is T max, that S equal to S sum, the condition is R2 by X2. This is the condition for maximum torque, right. So, the load increases, speed decreases, but slip increases and torque reaches the maximum value. So, this torque is called a pull out torque or breakdown torque or stalling torque, the torque at the maximum point. When further increase in the motor load, the speed decreases and slip increases and its value approaches the unity. So, it will, if you keep on increase the load, what will happen? The speed decreases and slip increases and the slip value will be almost unity, right. So, that we can see in the diagram. So, this is the maximum torque. Thereafter, if you keep on increase, the torque decreases slowly. At the time, the slip will be equal to 1. Here the slip is 0, here slip is 1, here this slip is corresponding to maximum torque, and also this is the maximum torque value. So, if you keep on load the motor, torque decreases and slip value become 1. Now, we will see analyze what will happen if the slip equal to 1. Slip is equal to 1 become what will happen. So, R2 square here is more, is very less than Sx2 square, right. This value is very lesser, this value will be more. So, that we can neglect the R2 square resistance value. In previous case we neglect the reactance value, now we can neglect the resistance value because this S is approaching to 1. So, this value will be more. In previous case the S is very less, while squaring it become very less, so that we can neglect this term. Now, S is equal to 1. So, when X2 square is more value than R2 square. So, we can neglect this R2 square. So, this is a normal torque equation, S R2 divided by R2 square plus Sx to the whole square. So, in this we are neglecting this R2 square. So, what will happen? S R2 divided by S square into X2 square. Now, we will go for further simplification. So, if you take R2 and X2 are constant, mean only we have S divided by S square, R2 and X2 become constant. So, the one S got cancelled. So, what we got? T is directly proportional to 1 by S. That is why the torque and slip are inversely proportional. So, that in the diagram we clearly noted that after the maximum torque during high slip region, the torque decreases. So, that relation is given clearly here. T is directly proportional to 1 by S. In low slip region, T is directly proportional to S, right. So, this is coming under high slip region. So, now as load increases, the speed decreases. So, the slip increases, but then T is directly proportional to 1 by S. So, the torque decreases, right. So, this curve is a rectangular hyperbola, 1 divided by S. Suppose if you be beyond the maximum torque, if you increase, what will happen? What is the conclusion? So, beyond the point of maximum torque, any further increase in the motor load result in decrease of torque develop. So, beyond the maximum point, if you increase the load further, what will happen? The torque will be decreases. So, the motor speed will slowly slow down and become stop. So, from that it is clear that we can load up to maximum torque, T max, S equal to Sm. Beyond that, the torque will decreases. So, we need to identify the maximum torque value. Up to that, we can load the induction motor, 3-phase induction motor. So, in this video, we discuss about the torque slip characteristics of a induction motor with two region, low slip region and high slip region. During low slip region, torque and slip are directly proportional. During high slip region, it is inversely proportional. And we conclude that beyond the maximum torque, the speed will, while increasing the load, the speed decreases slowly, so that the motor also motor speed decreases and become step down. The motor becomes stops. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening.